Could be introduction to gases. The PowerPoint start off with learning objectives. There are a lot here. You can read through those. But let's start off here.
So this PowerPoint's going to be on the gases side?
They already are. They're on Piazza, so you can just go download those on Piazza. When we look at gases here, we just take some observations of gases. So for example, here we have a gas sample in a container. The lid's being held down by two weights here. If we add a third weight, third weight's going to push the lid down further. So gases can be compressed. This is what it's showing. Gases, not only can they be compressed, but they can also expand. And so if we remove a weight here, the lid rise up. Not only that, if we remove all the weights, the lid reaches some point, equilibrium point, where the pressure inside here is the same as the pressure outside here. But we can make the pressure inside here even lower by pulling on the lid. If we pull on the lid, then we'll create what's called a vacuum. All a vacuum is it's a lower pressure than ambient pressure. So if the pressure in this room is, let's say, room pressure, then the vacuum would be anything lower than room pressure. And so these are just some general observations of gases. But for this particular chapter, what we're going to do is we're going to not follow the scientific method. The scientific method's already been done with the gases. The scientific method starts with what? Observations. So we have some observations here. And then from the observations we go to trends or patterns. And so the trends and patterns have been observed in gases, which leads to laws. And for gases, there are lots of laws, like Charles' law, Boyle's law, Gay-Lussac's law, the ideal gas law, the combined gas law, a whole bunch of laws. And from the laws, we move on to hypotheses and theory. And so this, this is kind of that multi-pronged approach to chemistry. That is, we try to mix in some observations with this is the theory. This theory, when we're describing gases in more detail, which is what theories do, and then we come up with something that they gave a name for. It's called kinetic molecular theory. We'll talk more about that later. There's a slide devoted just to kinetic molecular theory. But kinetic molecular theory, well, kinetic means what? Well, there's potential and kinetic energy. And they're kind of two different things. Kinetic describes the motion, right? Motion. And we know there are three types of kinetic energy. What are the three types of kinetic energy? We have three types of motion. Rotational motion, and what else? Rotational motion, vibrational motion, and translational motion. Now, if we just have gas here, in kinetic molecular theory, okay, it's the motion of molecules theory. Kinetic is motion, and molecular is molecules. But a gas need not consist of molecules. In this case, this gas consists of atoms. Here. And we have atoms in motion or molecules in motion. That's what makes up the gas. Now, for motion, if we have atoms like this, then atoms just have translational motion. We don't really think of them as having rotational. Rotational means there are different rotational energy levels. That is, there are different rotational energies. But in this case, the atoms are free to rotate, of course, but it doesn't really change their energy. And then vibrational, there's no real vibrational. These atoms are just going to have translational motion. Translational motion, they'll just travel from this point to that point. Eventually, they'll hit the walls of the container. And so, in kinetic molecular theory, we visualize a gas like this. It's mostly empty space with molecules, atoms, or even ions. When do you see gaseous ions? And do you recall what ions are? Excuse me. Ions are charged atoms or charged molecules. And they acquire charge through different processes. We'll talk about those processes later, but if we have charged atoms or molecules, we call those ions. They could have positive charge or negative charge. And if we have charged ions in here, then it's called a plasma rather than a gas. And so this is kind of like, here we look at some observational facts. In addition, we try to visualize these theoretically. Again, we're doing the same thing here. Here we have three states of matter. We have solid. For example, this iron nail is solid. If we look at the iron atoms here, how are they arranged? What kind of structure is that? Is it a molecule? Is this a molecule of iron? No, a molecule would have a discrete unit, an entity, but iron just keeps going in 3 dimensions. It doesn't really stop, so we call that one kind of structure. Yeah, crystal lattice, and so iron would be crystal lattice. The glass is also a lattice structure, but we wouldn't call the glass crystal, because it isn't as well ordered. We would call this lattice not a crystalline lattice, but a amorphous lattice or glassy. Sometimes people try to make glassy metals, because they might have unique properties that might make them interesting. So what they try to do is they try to freeze the metal quickly like a liquid metal to make it a frozen liquid, where the atoms are a little less organized. But anyway, this is a solid. Now, solid like this, there's motion there. What kind of motion does a solid have like this? Vibrational. Is there any translational? No. There's no translational. What happens is these atoms are stuck together. They're stuck together very tightly. It's very strong, like glue, or they're really sticky. So sticky we call it a bond, a chemical bond. That's unlike water. If we look at the water forms molecules. These are discrete units, H2O, 2 hydrogens, 1 oxygen. It's not like iron where it can go off in 3 dimensions and you just keep adding atoms. We could just keep adding water molecules, but we can't add like a half a water molecule or something like that in this case. And so here we have discrete molecules. The discrete molecules are stuck together. These are like sticky. Except they're not so sticky that they freeze the structure in place. I mean, they're sticky, things get stuck together, but there's translational motion available. And so they're free to move from point A to point B, except, they gotta be stuck together. And that's what holds the liquid together, this liquid. In a gas, the molecules, or the atoms, aren't stuck together at all. The particles are free to move. And so here we see some diatomic gas. It must be a relatively heavy diatomic gas, because if this were hydrogen, it should float in air, right? But this one's just sitting on the top of the surface here. Either the balloon's very heavy, maybe it's a thick wall, or it's a heavier gas than hydrogen. There are heavier gases than hydrogen, oxygen, nitrogen, etc. Okay. So here is, the macroscopic, and here's the particulate level. And we try to understand the particulate level in terms of theory. Anyway, which one of these three is the most dense? The iron nail, it's sunk to the bottom of the liquid. Then water, the gas. All right, since gases, there's a lot of empty space here. These particles aren't stuck together, and they're free to move. This is being shown here. And so, volume can contract, volume can expand. Not only that, we can easily form mixtures. We can form mixtures by adding. And so in this case, this green gas has been added. We have the red gas here. And so we can put any types of gas in this mixture. It should be no problem. And so gases can be easily mixed, like air. One thing that's going to result is this. We have to force this green gas in here because if we have this red gas here, then red gas is going to generate a pressure. the pressure is due to the collisions of gas particles with the wall. And so we have 3 gas particles here that are colliding with the wall. If we double that, now we're going to have 6 gas particles here. We're going to double the number of collisions with the walls. If we double the number of collisions with the walls, we've just doubled the pressure. And so we kind of have to force this in because it's going to be twice the pressure as this. But still, there should be no problem mixing it together. One way to reduce the pressure of the mixture is just make the container twice as big. If we make the container twice as big, then we're adding twice as many molecules, but we have twice as much volume. Therefore, the pressure is going to be the same. We'll talk more about pressure. When we look at the pressure in gases and liquids, gas pressure is exerted uniformly in all directions. So if we put a pressure gauge, at the top of the container, at the bottom of the container, and in the middle, we see no difference. The pressure gauge is reading all the same. This is due to the collisions here. The collisions can be at the top, the sides, or the bottom. They're random. However, in the liquid, if we put a pressure gauge, top and bottom, we'll see that the pressure gauge on the bottom is going to read a higher pressure than the one on the top. And one way of thinking about pressure is like the weight, the weight of the liquid. And so this is like a swimming pool. The deeper underwater you go in a swimming pool, the higher the pressure here. And the closer you are to the surface, the lower the pressure. And so liquid pressures vary depending on the depth. Gas pressures do not vary depending on the depth. Gas pressures are pretty much uniform throughout this container. Well, we jumped right to theory. And, where did this theory come from? This theory came from all these patterns and laws that people were trying to understand at a more fundamental level. So let's just jump to the theory. The theory, again, is called kinetic molecular theory, molecular motions, molecules motions theory. And these are the basic features of kinetic molecular theory here. Let's look at the first one. Gases consist of molecules in empty space. Well, gases consist of molecules and or atoms and or ions. It's not, so they're just using molecules generally. If we had helium gas, there are no molecules in helium gas. Helium just likes to form atoms. There would be atoms in empty space. So we can't take this too literally. But it pretty much consists of particles. Those particles can be molecules, atoms, or ions, and empty space. The volume occupied by the molecules in a gas is negligible compared to the volume of the space they occupy. In other words, this says the gas particles are tiny compared to the volume of the container. So it's mostly empty space in the container. Next, attractive forces among the molecules of the gas are negligible. Attractive forces are what holds things together. It's like, if we go back to this is a liquid. And if I look at the particles are about the same size here, let's say, maybe the same mass. And so what holds a liquid together? Some people say what holds a liquid together is gravity. So for example, if I have a liquid in this container here, gravity is holding it down here. But that's not correct. It's not gravity that's holding this liquid together. What's holding this liquid together is the surface. The surfaces are really sticky. And so the atoms get stuck together. Depends on how sticky they are. If it's really sticky, and we'll talk, sticky is not exactly the right word for it, but if it's really sticky, it'll form a solid. If it's really sticky, then there's no more translational motion. And so it can't be too sticky. As a liquid, the liquid's not too sticky, so the molecules can still translate, but the molecules or particles or the atoms are still stuck together. Here, they aren't that sticky. And so if they aren't that sticky, the particles can break free and form a gas like this. Mm-hmm.
Those dials?
Those dials are pressure gauge. And so the more clockwise it is, the higher the pressure. So it would be lower pressure, this would be higher pressure. So it's pressure gauge. And so basically, normally we think of zero. This is like a weight scale. If you get on weight scale here, and then that's it. And essentially what we are doing is, it is kind of a weight scale. When you're measuring pressure, you're measuring the weight. So for example, up here, are you measuring, is there much of weight of a liquid on you? No, but the deeper you go, the more those water molecules are going to weigh. Have you picked up a gallon of water recently? It's heavy. A gallon of water is like 8 pounds, more than 8 pounds. You know? And so think about this. The deeper you go, like for example, 10 feet in a swimming pool, 20 feet, 30 feet in the ocean. If you're diving 30 feet down, the water is going to get very heavy. So let's do the gravity as well. But here they're stuck together because so this is just kind of the weight scale. Here it's heavy, here it's light, here it's intermediate weight. So it says the attractive forces among molecules of gas are negligible. They're small, so the gas particles don't get stuck together. If the gas particles get stuck together, we call them liquid, because, and that happens. For example, steam. Does steam stay a gas forever? No. Eventually, what's going to happen is the water molecules can get stuck together and form little droplets, and the droplets will form little pools of water. So we'll get condensation. But anyway, they got to be relatively small, otherwise it would form a gas. The average kinetic energy of gas molecules is proportional to the temperature expressed in kelvins. And so temperature is a measure of the kinetic energy. Remember, we were talking about temperature and motion. Temperature is a measure of the motion, or kinetic energy. And when the motion stops, what happens to the temperature? So what happens is when the object's hot, we have a lot of kinetic energy, and as it gets colder and colder, we get less and less kinetic energy, and eventually the atoms stop moving. When the atoms stop moving, that's the coldest temperature we can achieve, and that temperature is called absolute zero, the coldest temperature. And so this is just saying that temperature and motion are related. Molecules interact with one another and with the walls without loss of kinetic energy. So when the molecules collide with each other, they don't lose energy. They don't get stuck together. Sometimes if you throw two soft clay balls at one another, they might stick together because they're kind of sticky, right? What they're saying is that's called an inelastic collision, where they kind of stick together. But what this is saying is they bounce off each other, like pool balls or billiard balls would bounce off each other. Those would be more elastic collisions. And so these molecules can collide with the walls and each other without losing any energy, or atoms. Right. All right. This is kinetic molecular theory. Now, what happens if the attractive force is, that is, these molecules are really sticky? Then the gas doesn't behave as nicely. And so normally what we do is we call this kinetic molecular theory of an ideal gas, because there's variations on how sticky gases are. There are variations on how big gas particles are too. And so those can impact things as well. And so this is not the complete theory. The complete theory is much more involved. So this is basic. All right, in steam, well, the water molecules are stuck together in liquid water. But if you increase the temperature, then what happens is you have enough kinetic energy, you can break these water molecules apart and form steam. And so if we heat water up, we form steam, or if we break them apart. But one thing about gases is the gases are about 1,000 times less dense than liquids. Do you recall the density of water? The density of water is an easy number to remember. The density of water is about 1 gram per cubic centimeter. And so milliliter of water weighs 1 gram. Now, is that exact or is that approximate? It's not exact, it's approximate. It's the 1 sig fig, 2 sig figs, or 3 sig figs is good. And so the 3 sig figs means 1 milliliter of water, or 1 cubic centimeter, weighs 1.00 grams. Now, if you went to 4 sig figs, it's no longer good, because at 4 sig figs, it's actually 0.9998 grams. You know? And so if we round that to 3 sig figs, we're okay. Well, anyway, this is about 1 gram per milliliter. Now, gas has a density about 1,000 times less. So if this is 1 gram per milliliter, this would be 0.001 gram per milliliter, or 1 gram per liter. And so in other words, one other way of thinking about this is if we have 1,000 molecules here, we would only have 1 molecule there, right? Because if it's 1,000 times more dense, we'd have 1,000 times more molecules. And so if we count these, we should have 1,000 molecules here and just 1 molecule in all of those here. Now, let's talk about pressure. There are different ways of thinking about pressure. One way of thinking about pressure is it's the force of the collisions on an area. So normally when we think about pressure, you know, we think about the particles colliding with the wall. So we'll have some kind of wall here, and then we'll have a gas particle collide with some force. And so we pick a unit area, this is the unit area, and then figure out the force of the collisions on there. And so this is, you know, this is easy. For example, if there are no particles in there, there are no collisions. If there are no particles in there, then what's the pressure? 0. There's no gas in there. If there's no gas in there, we call that a perfect vacuum. Perfect vacuum. Perfect vacuum, there's no gas, therefore there's no collisions, therefore there's no pressure. And so we get 0 pressure. And then if I add more and more gas, you know, I'll generate more and more pressure, depending on how many. So if I double the number of particles, I'm going to double the pressure. So I'll get twice as many collisions. If I triple the number of particles, I'll triple the pressure. There. That will impact pressure. Another thing that impacts pressure is temperature. So, for example, if I increase the temperature, the molecules and atoms are moving faster. If they're moving faster, then their collisions, the force of the collisions are going to go up, meaning the pressure is going to go up. If I cool it down, the pressure goes down. If I change the area, you know, I put all the same number of molecules but in a smaller area, then the pressure is going to go up. And so these are the types of things, like the volume. If I force more gas into this, pressure goes up. If I remove gas by sucking it out using the vacuum, pressure goes down. So those factors influence. We aren't going to do any math with this equation. Just showing force there. Well, let me talk about this. Another way of thinking about pressure is weight. You know, not these collisions, but the weight. If this is some big mountain here, going down to sea level down here, let's say, sea level. Let's see. If you're standing at sea level here, like, yeah, we're close to sea level here, is the air weightless here? Does the air weigh anything? What do you think?
It's negligible.
The weight of the air is negligible. Do you feel the weight of the air on you? Yeah, you don't feel it because you're designed to have it. You would feel it if there was no air. You know, if you went into a vacuum, you would be in big trouble. Like me, I would be in big trouble too. Everybody would be in big trouble in a vacuum because we'd be like a balloon. You know, have you seen a marshmallow in a vacuum?
Yes.
No. Do you want to see a marshmallow in a vacuum?
Yes.
Yes.
Well, I don't have it set up. I just have to show you video. Sorry, but I'll set it up. Marshmallow. Back. Well, the marshmallows are produced under the weight of the air, you know. And when the weight of the air disappears, this is what happens. Like a marshmallow, we are produced under the weight of the air too, so we're kind of used to the weight of the air there.
Marshmallow.
Hold on.
Peep. My clean plate. Put in a Del jar. Hooked up to a vacuum pump. Flip it on.
That's a noisy pump. That's not even a very powerful pump. That's a weak pump. Sorry.
Close the valve. Disconnect.
That's like Thomas Edison.
There we go.
So now it's back to normal.
It looks sad.
There's our peep marshmallow action. Good stuff.
All right. So when you suck out the air there, then you lose the weight of the air. And so actually, you know how much the air weighs at sea level, approximately? It weighs 14.70 pounds per square inch. Yeah. And so if we're here, we have 14.70 pounds of air. And that 14.70 pounds of air is the blanket of air that we live in, the atmosphere. And so it's the weight of the atmosphere on your body. Now, if we go to higher elevations, are we going to have 14.7 pounds of air on top of us?
No.
No. And so if we go to the top of the mountain, we're going to have a lot less, like a third or a half or 3/4 or something like that. You know, the pressure is going to go way down, like a top of Everest or something like that. And so it was a little bit wrong. You know, originally it said that the air pressure is uniform or the gas pressure is uniform in the container. It depends on how big the container is. If you have a very small container here, if I have a small container of gas here, then the pressure is uniform throughout this. But if I had a very large container like this, then the air pressure acts like a liquid in a way. You know, the bottom of the container is going to be at a higher pressure than the top of the container. Just like in a liquid, if I look in a liquid, liquids behave like this. At the bottom is going to be heavier than at the top, so there's going to be a higher pressure at the bottom. And so it's not exactly correct. I mean, if we had a gigantic container, then the air pressure is not uniform. This is due to gravity. It's due to gravity because the heavier molecules and the heavier particles are going to be down here, and more of them are going to be here. The lighter ones are going to get up here. But over a small volume, it's uniform throughout. And so we got 14.7 pounds per square inch of air. Actually, is that a lot? It doesn't seem like a lot, but it's a lot. 14.7 pounds is a lot because, you know, to get 14.7 pounds per square inch of water, you know, how much water would I need to get 14.7 pounds per square inch of water? So if I had a square inch and I wanted 14.7 pounds, do you know how much water that would be? That would be close to 30 feet of water. And so, in other words, it's like this. If I'm 30 feet underwater here, then I'm going to have 2 atmospheres, right? I'm going to have 14.7 pounds of water plus 14.7 pounds of air. We call 14.7 pounds an atmosphere. And so here at sea level, I'm about 1 atmosphere. And then at 30 feet underwater, under liquid water here, I'm at 2 atmospheres total of pressure. So this is liquid pressure. And plus the gas pressure. In other words, it's the weight of the liquid or weight of the gas. Sorry, I need to turn this on. All right, so let's take a look at this. Now, how do I measure the weight of the atmosphere here? You know how I measure the weight? We use like a triple beam balance. Can you measure the weight of the air with a triple beam balance? If I set a triple beam balance on the countertop, can I weigh the air 14.7 pounds? Why not? Well, because it'd be pressing 14.7 pounds here, and it'd be pressing 14.7 pounds here. But it's a gas, so it's tricky. It's tricky to do that. But it's done in this way. And so, how do I weigh the air? Well, how I weigh the air is with a barometer. And the barometer acts like a triple beam balance in this way. You know, and a triple beam balance, or actually, it just acts as a balance. Basically, it's this. We have one pan, we put the air, the atmosphere on. And in the other pan, we put the weights. Now, what should we use for the weights? Well, the weights, we don't have like solid weights, you know, that you chunk over. In fact, it's going to be a liquid. What we're going to use as a counterbalance is a liquid, and it's a very heavy liquid. Like, for example, water. You know, water has a density of about 1 gram per milliliter. What's the density of gold, roughly? Not 2. 20, yeah. 20 grams per milliliter. What's the density of lead, roughly? Lead is about halfway between water and gold, right? 11 grams. What's the density of mercury? Is mercury closer to gold or closer to water compared to lead? Closer to gold. Mercury's density is about 13. And so the way this works is this. If you had a swimming pool and you wanted 2 atmospheres of pressure, let's say, you know, you'd have to make a 30-foot deep swimming pool, right? And then you'd have the blanket of air plus the blanket of water. But if you made that swimming pool out of mercury, it wouldn't have to be very deep. To get 14.7 pounds per square inch of mercury, do you know how deep you'd have to go? Or how tall it would have to be? It'd just have to be 3/4 of a meter. If you had 3/4 of a meter, then that's it. Problem is sinking in mercury. You know, you wouldn't be able to sink in mercury because you're not dense enough to sink. You float on the surface of mercury. So what you'd have to do is you have to have like gold. You'd have to make gold weights. You make gold weights so that you can sink. So you get a whole bunch of gold weights around you and then sink. And then sink about 3/4 of a meter into mercury, and then you'd have about 2 atmospheres of pressure versus 30 feet underwater. Right? And that's because mercury weighs. And that's good because, think about it. If we had to make a barometer out of water, the barometer would have to be like 3 stories tall. Because we'd need, you know, you'd need 14.7 pounds of water, and you need it to go 3 stories or 30 feet tall in order to counterbalance it. So it'd be a weird looking balance. You know? But in this case, if we use mercury, then we only need about a meter of height, and then we can measure it. And so basically it's going to work like this.
It's just this kind of relates to what you said, but I know you said like, right now when you said like weights with the gold and anything, of how gold like dissolves in mercury, like how does that work?
Gold forms alloy, amalgam with mercury. And so another way of thinking about it is the gold really doesn't dissolve in mercury. The mercury dissolves in gold. Because when mercury dissolves in gold, it forms a solid alloy. And so it's just a mixture. And so the mercury gets incorporated into the gold lattice. That can often happen with the alloys because a lot of these alloys, their solid lattice structures are the same, just the atom size is a little bit different. And so you could easily substitute different atoms for other atoms. Like, for example, silver can easily substitute in the lattice for gold but the size of the atoms are a little different, so it's not the perfect lattice. But we can have things like that.
Okay, thank you.
Well, anyway, so this is like a balance here. Right now, one way of thinking about this balance here is which side weighs more. So let's say we have the atmospheric pressure here, right, pushing down. In here, there's a vacuum, so there's nothing pushing down. A vacuum, you know what a vacuum is? A vacuum is empty space. There's no gas in there. A perfect vacuum has no gas. Therefore, there's no collision, so there's no weight.
Is the air pushing the mercury upwards?
Yeah.
Is that how it's measured?
Right. The air is pushing mercury upward. And so, in other words, we get a situation like this. But the way we visualize this is we visualize it as a balance, like a triple beam balance. We try to get the two levels equal. And so here's a pivot point. And so we have the weight of the air on this side. And on the other side, we have the weight of the mercury. And so in this case, the weight of the air is equal to the weight of the mercury. Well, we can use physics to calculate, what the pressure of the mercury is. And in physics, we have units of force, newtons, and we have units of area, meters squared. And so the pressure is typically given as newtons per meter squared, which is called a Pascal. But that's a hassle. And so we don't actually do the calculation. We could calculate, what is the pressure of the liquid mercury here, but we don't because to calculate the pressure of the liquid mercury, we can use an equation in physics. The equation in physics is the pressure is equal to the density times G. You know what G is? Gravity times H, the height. The higher or the deeper, the higher the pressure. And so the density of mercury, does it really change? Does the density of gold change, fluctuate much? No. Same thing with the density of mercury, it doesn't fluctuate that much. And so we say the density of mercury is a constant. How about G, the gravitational force, whatever, gravitational constant we call it. It's called 9.8 meters per second squared. That doesn't change. The only thing that changes is the height. And so this is the lazy person's approach. The lazy person's approach says, I'm not going to bother calculating the pressure. The only thing that's going to change when we're dealing with the liquid is the height. And so rather than saying I'm at 2 atmospheres, if you're 30 feet underwater, you'd say I'm at 2 atmospheres of pressure because you got 1 atmosphere of air plus 1 atmosphere of water. So technically you're at 2 atmospheres. But rather than saying that, you take the lazy person's approach and you say, I'm at 30 feet underwater pressure. Okay, so I'm 30 feet underwater pressure. That's 30 feet of water. That's the pressure. If I'm 45 feet, that's 45 feet of water pressure, right? That's the lazy person's approach. Well, that's the approach we're taking. Rather than figuring out what pressure is, we're going to say, well, I'm 760 millimeters of mercury under that depth of mercury. That's the pressure I'm at. And that just so happens to be 14.7 pounds. In other words, that happens to be 1 atmosphere. And so with pressures, we often use height or length rather than the actual pressure. It's not correct. We'd have to correct it. The easy way to correct it is just to use conversion factors or to actually calculate the pressure. But this is a barometer. And so the pressure fluctuates depending on the weather. You know, if a storm is moving in, then it's kind of low pressure. But how low pressure? It just changes millimeters here. You know, it's not a huge. If we go to the top of Everest, then there's a pretty big change in atmospheric pressure. But around sea level, it's going to fluctuate up and down like this, maybe plus minus 10 or so, you know, depending on the weather. A bright sunny day, we're well above 1 atmosphere. But essentially it works like a balance here. Now, pressure is one of the important things we want to know about a gas. When we're taking observations of gas, what types of things do we observe about a gas? We observe the pressure. We can measure the pressure. That's barometer is one way, the other way. We are concerned about the volume of the gas. You know, how much gas do we have? The amount, you know, the amount is like this. If you buy 1 liter of helium, you know, well, 1 liter of helium can mean a lot of different things. Usually when we buy gas, you don't buy it by volume. You know how you buy it? Like if I'm going to buy some helium, I don't say I want 10 liters of helium. Like you go to gasoline, you buy gasoline, you buy it by the gallon, right? You wouldn't do that for gas. You know why? Because the pressure, I mean that 10 liters of helium could barely have any gas in it. And so what we do is we buy it by weight. You know, that 10-liter cylinder of helium, how much does it weigh? Does it weigh a lot? Is it heavy? Then we know lots of gas is in there. If it's very light, like a balloon, then you aren't getting much helium. And so you gotta. This is why we're concerned about the amount. You know, the amount. Normally people think about the amount as volume. You know, but for gases we don't. Then we have temperature. We want to know the temperature of the gas as well. So these are the typical things, properties that we observe. This is a little bit out of order, but this is the order in the book. Now, when we're observing pressure, we have different units that we use. The common one is the atmosphere, the ATM. 1 atmosphere is kind of the average pressure at sea level. You know, it fluctuates up and down. And that's 14.70 pounds per square inch, which is equivalent to 760 millimeters of mercury, which is equivalent to about 30 feet of water. (760 millimeters of mercury is also called 760 torr. In other words, a millimeter of mercury is the same thing as a torr. This is named in honor of Torricelli, who did some early work with gases. If we wanted to calculate the pressure, you know, like I said, we could calculate the pressure because if I wanted to figure out the pressure of the mercury, I can. It's just the density times G times H. When I do that, the units I get are called Newton meters, Newton per square meter. And so if I actually did the physics and calculated, then 1 atmosphere or 760 millimeters of mercury is equivalent to 101,325 newtons per meter squared. A newtons per meter squared is called a Pascal. So Pascal is the common physics unit of pressure. A Newton is a unit of force. You know, the more newtons, the more force you have in the collisions. What do you need to know from this? What you need to know is this middle one here. You should know that 1 atmosphere is the same as 760 millimeters. In fact, it's defined. It's a kind of definition. It's exact. This one you don't have to know. I don't think we're going to do much with Pascals. Bar. 1 bar is 100 kilopascals, or 1 times 10 to the 5th pascals. A bar is very important because now there's a big push to switch to bars. People are trying to get the U.S. to convert from atmospheres to bar. You think that's going to happen? I'm not very optimistic. This is like that big push to the metric system. I don't know if you're aware, but the U.S. was going to adopt the metric system, and
Why didn't
I think it's just too costly because everything would have to switch, all the bolts and everything else. Now everybody has to buy like 2 sets of tools, one for the metric and one for the inch. Yeah, something like that. It'd just be too complicated. And so we're both. We can go either way. It's good. And so going on here, bars. Well, one thing about a bar and an atmosphere are about the same. And so if the weather, report says that the pressure is about 1 bar, then it's about 1 atmosphere. It's just slightly different. Not that much. Then we have pounds per square inch, 14.70 psi per atmosphere. Anyway, 760 millimeters, if we convert it into inches, there are 2.54 centimeters per inch. We can use that and calculate 29.92 inches of mercury. Is equivalent to 760 millimeters. So that's just a millimeter to centimeter to inch conversion. All right. None of these you have to have memorized. There are lots of ways of measuring pressure. Barometer is one way. Barometer is usually meant to measure barometric pressure. Barometric pressure is just the air pressure outside. It's not meant to measure a gas sample. Let's say I had some gas trapped in here. I want to know what is the pressure of the gas in here, or in a soda bottle or something like that. What's the pressure of the gas? We can't fit a barometer inside this container here. And so usually we use a different device. One of the early devices that have been used to measure gas samples is a manometer. So we have barometer, which measures barometric pressure. We have manometers, which measure gas sample pressure. A manometer and barometer work in much the same way. It's a balance. And so let's take a look at a manometer here. A manometer is this. It's a U-tube like this, filled with mercury, liquid mercury. I have some liquid mercury I'm going to bring in. It's very heavy. And so we have a U-tube like this, and we think of this like a seesaw or balance. The pivot point's in the center here, so it looks like what happened is one end went down, the other end went up. And so I have this, I have the weight of the yellow gas here pushing on the surface of the mercury. What's pushing on the surface of the mercury here? Well, if we go up, it's open. If this is open, this is why it's called open end manometer. It's open to what? Air. And so what's pushing down on here is the barometric pressure. And so let's say the barometric pressure were 14.7 pounds psi. And so that means there's 14.7 pounds pushing here. That means what's pushing here must be greater than 14.7 pounds, equal to 14.7 pounds, or less than 14.7 pounds. This is the balance. It's like this. On the left, I put 14.7, on the right, I put 14.7 pounds. On the left, I put greater, less, or equal. It's got to be greater. In other words, if you have 14.7 pounds here and it's pushing down like this, then this side's got to weigh a lot more. And so in other words, the weight of the gas or the pressure of the gas here has got to be a lot greater than 14.7 pounds or 1 atmosphere. That is if this is 1 atmosphere. Let's say 1 atmosphere is pushing there. This has got to be more than 1 atmosphere pushing here. This gas is under pressure. Well, how much pressure? Well, how much pressure is, we can do a calculation. We'll have to do a calculation. What we do is this. Rather than leave the balance like this, we're going to bring the balance level. If we bring the balance level, then what's pushing on the left here is the pressure of the gas. What's pushing on the right? Well, what's pushing on the right is, you have to think like the swimmer. The swimmer's got all that weight of the air plus the weight of the liquid, right? And so if you're down here swimming in this pool of mercury, then you got to think, you got this much mercury here weighing on you, plus the entire atmosphere of air weighing on you. And so, in other words, well, the atmosphere of air, we just use the barometer to measure it. And when we use the barometer, we do it indirectly. We measure the height, right? The height of the mercury, liquid mercury. Well, how high is it? How many millimeters is it? And so from the barometer, we're going to get millimeters of mercury as the pressure. And then from this, well, this is already mercury. This is liquid mercury. So all we do is we take a ruler and measure how many millimeters of mercury do we have here. And then we just add the 2 millimeters of mercury up, and then we have the total pressure in millimeters of mercury here. So let's say, for example, this were 760 millimeters of mercury. Then this gas must be 2 atmospheres, because I have 1 atmosphere here, or 760, and we have another atmosphere here, or 760. And so altogether, that's 2 atmospheres pushing here, and therefore this gas must be at 2 atmospheres. Does that make sense? And so this is what we call an open-ended manometer. In this case, this is a little different scenario. In this case, which weighs more, the gas or the atmosphere? The atmosphere weighs a lot more. And then, well, how much more? Then we can figure it out. So what we'll do is we'll level out the seesaw. And so on this side, we have the weight of the atmosphere. On this side, we have the weight of the gas and the weight of the liquid mercury. And so we would measure the weight of the liquid mercury by measuring its height. And then all we do is this. We subtract. And therefore, the pressure of the gas is equal to the atmospheric pressure minus all this, the weight of the mercury. And so we either add or subtract. So we'll do some manometer calculations later. But this is basically it. It's a manometer used to measure gas pressure. Actually, they show it here. So the pressure of the gas on this side, the weight of the gas is equal to the weight of the atmosphere plus the weight of the mercury. Okay, the weight of the gas here is equal to the weight of the atmosphere minus the weight of the mercury here. Take it out. All right, sometimes we want to do some straight conversion with the pressure unit. And the pressure units depends on who's measuring the pressure. People have preferences. Some people like PSI. Some people like millimeters of mercury or torr. Some people like atmospheres. I like atmospheres myself. But the pressure inside a steam boiler is 1,427 psi. It expresses pressure in atmosphere. So this is an example of what type of problem, the dimensional analysis problem. Why don't you go ahead and do this calculation and let's see. Have you ever picked up a lead brick? This is a lead brick. A gold brick would weigh about twice as much. But if you want to pick up a lead brick, it's here. Lead brick. Mercury would weigh even more. Not much, but a bit more than that. So did you get the answer? Does somebody have it? Just curious. 97.1?
Yeah.
7.07.
No, a 4, it's just 4, significant figures, so.
Yeah, there's
it's
4 significant figures.
47.07. 97.07.
97.07. Okay, that's the way the book does it, but I don't like it done like this because if you do it like this, I don't see what the drop digit is. I want to see the drop digit. And so I want it written 97.074. Okay, or 48. But we would write 97.074, at least show one digit. And then we don't round until, we only have one rounding step. So we're going to drop the 4 and then it'll go to 97.07. So that's good. All right, let's stop here. We're going to take a break and then we'll start again.